evening and welcome to tonight's special event. Hi, I'm John Beacom. I'm the director of the Center for Cosmology and Astroparticle Physics. I'm your host. This Center for Cosmology and Astroparticle Physics is dedicated to exploring the universe and all of its amazing contents, training students and postdocs on the next generation of science, and most important, bringing the exciting results to the public. So one of the things that we do for that is have a series of public lectures. This is one. And tonight we're delighted to welcome two very distinguished visitors. First is Professor Daniel Whiteson from the University of California at Irvine. And the second is Dr. Jorge Cham from PhD Comics. And so without further ado, let's welcome them in.
How's it going? You guys don't sound very excited. I'll try it again. Midterms. I'll try it again. How's it going? All right. Not much better. But I will take it. We'll go with it. Well, first of all, I want to thank John and the physics department for inviting us here tonight and organizing this event for all of you. Let's give them a big round of applause, please. And also, thank you to all of you for coming to the event tonight. I know it's Friday night, 7 p.m. It's a beautiful night here for Columbus. And I'm sure at 7 p.m. on a Friday, most of you would much rather be, in the lab, in your offices, working hard, starting your day of work. But instead you came to hang out with us, so thank you very much. So my name's Jorge Cham, and I'm here with Daniel Whiteson, and together we are the authors of this book called We Have No Idea. Now I'm a cartoonist, and to me, cartooning is about taking a blank page and filling it with an idea. And so the idea we want to draw out for all of you here tonight is this idea that there are still big gaps in our knowledge of the universe. Now, in addition to being a cartoonist, I also happen to have a PhD in robotics. Now, you might be wondering, what does having a PhD in robotics have to do with being a cartoonist? Well, I can tell you that my parents are also very concerned about that life plan there. But yeah, so tonight I'll just kind of tell you a little bit about how Daniel and I got to work together and how we ended up working on this book. And then Daniel's going to come up here and I should tell you about all of the ideas inside of We Have No Idea. So the story is that, I was a PhD student at Stanford University, and I was there for about a number of years. But my thesis, my research there focused on robotics that could run and walk, and specifically it focused on these small robots that could run like cockroaches. And so here's a quick video of what these robots look like. Yeah, that was my PhD thesis. And, I like to show this movie at every presentation I give for two reasons. First of all, I feel like this movie, it really kind of captures what it feels like to get a PhD. Some of you might know the feeling, right? You feel like you're running the whole time, but you're not getting anywhere. Meanwhile, there's a more intelligent being stamping you down. But I also like to show this movie because it's really the only way that anyone will look at my research anymore, because it's become a little clearer that a little bit more popular than the research I spent years working on as part of my actual career, a little bit more popular has been what I was doing when I should have been doing research, when I was procrastinating, which was to make these comics called Piled Higher and Deeper, or PhD comics. Now, these are comics that I just started drawing as a grad student, and they were kind of about the experience that I was having of, for example, talking to professors and begging them to take you on. The comics were about being a teaching assistant. Right, and having to deal with those annoying undergrads. Oh, I hope there aren't any in the room here. I'm sure you're cool. Yeah, let's see. The comics are also about grad student etiquette. Never ask a grad student how their research is going. That's just rude. So yeah, I just drew these comics for the newspaper there, and then one day I decided to take my procrastination to the next level. And I started posting all of these on a free web server on the Stanford campus. And I think what happened was people who read it there and liked it would then tell their friends that they knew in other universities about the website, and then those people would then tell their friends and cohorts and lab mates, and those people would tell other people in other universities. And so slowly over the years, kind of like a virus, these comics kind of went out into the world. And so to the point where about these days, about, like 4, 5, 6, 7 million people a year visit the PhD Comics website, which is a really small number. If you think about the fact that there are 7 billion people on this planet, so there's about a 1 in 1,000 chance that you might have seen these comics before. But it just so happened that one of these 1 in 1,000 people that were reading the comics was this professor at the University of California at Irvine, Daniel Whiteson, who one day decided to write me an email. So one day I wake up and I check my email and I get this message from this professor saying, Jorge, hey, I've seen your comics online. I think they're pretty good at explaining things. I'd like to pay you, I'd like to commission you to draw some comics about the Higgs boson. And I thought, what? You want to pay me? What is that? I don't understand it. I just put things on the internet for free. But he said this was around the time before the Higgs boson was discovered, and there was a lot of attention in the media and articles and newspapers talking about the search for the Higgs boson. But Daniel saw these articles, and he didn't feel like they were doing a very good job of explaining what it was, why they were looking for it, how they were looking for it. And so he decided to take that initiative and use some of his discretionary budget to hire a cartoonist to draw something that explains to the public what the Higgs boson was. And so I thought, how much is he paying me? And I said yes, and I drove down to Irvine, and we talked for like 4 hours out there in the cafeteria, and I recorded our conversation. And so then when it was sort of time to actually draw these comics, I decided to experiment a little bit. And not only did I draw the comics, but I sort of took that audio of our interview and I edited it, and I sort of recorded myself drawing the comics, and we made this kind of combination video and comic, which I'm going to play for you now, just a couple of clips from that video, just to give you a sense of how our collaboration started.
So one of the things people predict is the Higgs boson. The idea is that the Higgs boson is the particle that is responsible for giving mass to the other particles. So you think of things that have mass means it has stuff to it. It's not actually stuff. Earlier I was saying an electron has mass, but has no volume. How can that be? Mm-hmm. Turns out mass is probably just a characteristic of a particle the way like charge is. Like some particles have charge, like electrons. Some particles don't. It's just a different kind of charge. So you can think of mass as sort of gravitational charge. And when two things both have mass, they attract each other. Okay. Interestingly, you can't have negative mass or repulsive gravity. So the collision happens. It lasts for like 10 to the negative 23 seconds, and you get one measurement, right? So if you say, well, I'm going to plot the mass, the total energy of this guy. I'm going to add this guy and this guy together and add the total energy. This is this axis here is number of collisions. You do an individual experiment, you get one measurement, right? Here. You do another one, you get another measurement. You do another one. Eventually you build up your data, right? And the data looks like this, for example. And then you have two theories, right, that predict the data. One says, well, I'm going to predict there's no Higgs boson, so the data should fall along this line. And the other is I'm going to predict that plus a Higgs boson. And the problem is the difference between these two theories is very small. And so it's very hard to distinguish these two with our data because the predicted effect is tiny, right? If the predicted effect were huge, it'd be very easy to tell the difference between with Higgs boson or not with Higgs boson. But the predicted effect is tiny, and so it's really hard to see. What you need is a huge amount of data. You need to take a bajillion collisions before you can see the difference. That's why we run this thing 40 million times a second, all day, all year, to get a lot of collisions to tell small differences between theories. It's like when you take a picture of the sky. If you just take a picture, you get a little bit of light. The longer you leave your telescope looking at the sky, the more you can see farther away things.
Cool, yeah. That was the video. And so we worked in it, and we kind of decided to take a risk, and we just put it out there on YouTube and on the PhD Comics website. And what ended up happening was that people liked it. A couple 100,000 people watched this online, and they enjoyed it. And but then what was even crazier was that they actually discovered the Higgs boson a couple of months later, and then the video really exploded. Millions and millions of people saw this video. It went viral. They read the comics. And a lot of websites like the New York Times, CBS News, they were all pointing to this video as the easiest to understand, most clear explanation of what the Higgs boson was, or what this interesting complex phenomenon was. And so I thought that was pretty cool, that the clearest and most easiest to understand explanation of this complex phenomenon didn't come from a reporter at the New York Times or a media person at CBS News. It actually came from one of the scientists who worked on the project, who decided to take that initiative to create something that communicated that to the public. So I thought that was pretty cool, and so I always encourage all of you scientists and academics here in the room to take that initiative and really try to take matters into your own hands to communicate what you do to the public. So anyways, that was our first project together, and then we've done a couple of others, but the latest one is this book called We Have No Idea. And so to talk to you about We Have No Idea is Daniel Whiteson.
All right, good evening, everyone. Thanks again for coming out. It's a real pleasure to be here, and it was also a real pleasure to work with Jorge on this book. He tells that story about how this collaboration got started. He leaves out a little detail because he's too modest. Anybody who's in academia knows that Jorge is not just some online comic. He's like a famous online celebrity. I mean, let's be honest about it. I go and I visit a lot of physics labs and biology labs. There's almost always one of his comics up on the wall, one that captures like the angst of the graduate student experience, right? It's like he's done collective therapy for everybody through the comics, It's wonderful. Anyway, when I was thinking about doing, explaining physics with cartoons, I don't have any artistic talent myself, so I couldn't draw them. And my wife, who's also an academic, she said, why don't you email Jorge Cham and ask him to do it? I thought, yeah, right. After that, I'll email Brad Pitt and I'll ask him to do a movie about me also, right? Well, Brad hasn't gotten back to me. But here I am doing an awesome project with Jorge, which has really been a wonderful experience. All right. So our book is called We Have No Idea. And the reason that we called it that is that it's not about the things that science has figured out. There's a lot of popular science books, which are really excellent, that explain what science has learned. And it's learned a lot. But the point of our book is the opposite. Our point of our book is to explore what science hasn't yet figured out, what we don't yet know. So that's what our book is about. Now, if you come to hear a talk by an author of a science book, you expect to hear from an authority on the topic, right? You go to hear a book about flies and genetics, you want to hear from a fly geneticist, right? So if this book is about not knowing the answers to questions, you might be wondering, well, what's my expertise? Am I like a special expert in ignorance or like not having ideas or something? So it's not that I want to claim any special expertise in ignorance over anyone else. It's just that I want to convey to you the excitement of our ignorance, because our ignorance is opportunity. It's opportunity for discovery, to discover basic, mind-blowing facts about the universe that we still don't know. All right, and it really comes out from when I was a kid, and I was learning about the age of explorers, and I thought, that was pretty cool. These guys could just jump in a ship and sail across an ocean, and they could land on a new beach, and they could have an experience nobody had ever had before. They could be the first person to walk on a beach, or the first person to taste a new fruit, and I thought, that is an incredible experience, to be at the forefront of human knowledge, right? And I wanted that for myself. I thought, what was it like to be the first person to ever see the Grand Canyon, right? Somebody got that as a first experience. Or the first person to ever eat chocolate, right? Somebody got that. Or the first person to ever eat chocolate while looking at the Grand Canyon, right? These are all important firsts in human history, and as a kid, I wanted one. It seemed really exciting. But as you read about the Age of Explorers, you kind of get disappointed because on the one hand, it was exciting. On the other hand, it feels kind of used up, right? There aren't any more continents to land on. Thanks to Google Earth and satellites, there are no more little islands to discover and name after your dog or something like that, right? You might feel like the age of exploration is over. And as you look around you at the amazing technological marvels brought to us by science, you might be convinced that science has most things figured out. After all, we have incredible airplanes that can fly you across an ocean, right? We have all of human knowledge can fit on a tiny little device that you could have in your pocket and access almost anywhere in the world. It's incredible. You know, truly we live in an age of wonders. And a scientific era where Brad Pitt really has no excuse not to call me back. I mean, come on, Brad, call me back. Anyway, so you might be forgiven for feeling... He'll change his mind. He'll see. You might be forgiven for thinking that science has it mostly figured out, that it's just a few little details, right? We've made so much progress, and it's just a couple little things here and there we have to figure out. So the point of our presentation tonight, and the point of our book, and my personal passion in science, is to explain to you that the exact opposite is true. That I think we're at the beginning of a new age of exploration, a new era of incredible discovery that will change the way we look at the very universe, at the human context, at the basic nature of the human experience, okay? Really, really big questions are not yet answered, right? And that's what this is about. This is why I have the clicker, see? Okay, so if I'm talking about a new age of exploration, what kind of exploration? Because you can't get on a ship and find a new island, right? That is done. However, there are new things to discover. And the things that are left to discover are the answers to really big, fat questions. What do I mean by a big, fat question? I mean the kind of question you don't need to be a scientist to want to know the answer to. The kind of question, if you knew the answer, it would change the way you felt about life as a whole, right? So if you walk down the street and you ask people, what's the most important question? Or what one question would you like to know the answer to? You might get questions like this. Why are we here, right? That's a classic. If you knew the answer to that question, it would certainly change the way you lived your life, right? Or what happens after we die? Definitely, I would like to know the answer to that question, as would everybody. And if you did, you might live differently, right? Here's one that's often discussed. What is it like to be a bat? Okay? And if you think, oh, that's certainly a joke, they're just being silly. It's actually the title of the most widely cited philosophy paper of all time. Okay? People talk about this, and they're still talking about it. And that's kind of the problem. In the halls of philosophy, they talk about these questions, but they don't really find answers, right? These questions, you can smoke banana peels with the philosophers for 20 years and talk about it. You don't necessarily get anywhere. Because these questions don't have hard and fast answers. I mean, they're big questions, they're important questions, I don't mean to dismiss them, but they don't have answers that we can't disagree about. To me, what's exciting is that there are other questions in the same category, questions like these, that are just as important, just as earth-shatteringly important, but these are science questions, right? Questions like, what is everything made out of? Or, how did the universe begin? After all, the universe has a single true history, right? It started in one way and in no other way. And if you knew exactly that story, that might change the way you felt about your life, depending on what the answer is, right? People have been wanting to know, how did the universe come into being? What are the initial moments of the universe like? They've been asking that question for thousands of years. Someday, we will know the answer to that question. The answer exists. It's out there as a fact, right? And if we can figure out how to be clever and sift through the rubble of the Big Bang in just the right way, we can get the answer. We will get it, or our children will get it, or our children's children will get it, assuming science survives this age of idiocy, right? We will figure this out. So the answers are there. And to me, that's exciting because those answers will change the way we look at the universe. All right, so I devoted my professional career to answering this question. What is the universe made out of? And to me, it seems like a pretty basic question, right? It's a fair question to ask. You emerge as a conscious being in the world and you wonder, what am I made out of? What is this floor made out of, right? How does this whole thing put together? It also seems to me like a pretty ancient question, right? I imagine people have been asking this question since people have been asking questions, right? All you have to do to think about this question is take two rocks, bang them together and get smaller rocks, and then take those rocks and bang them together and just keep going. And eventually you wonder, and I remember asking myself this question as a kid, how long could I do this for? Do I eventually just get infinitely small rocks? Or at some point, does it start turning into something else that's not quite rock, right? So maybe it's no surprise I became a particle physicist, right? And I like to imagine that this is the particle physics superhero creation myth, right? This is when particle physics was born. And so I think people have been asking this question for a long time, even before superheroes wore capes. And imagine that you were the first person to think of this question. Okay, this is a big question. Imagine you were the first person to ever conceive of it and ask yourself this question: what is the universe made out of? If you were a caveman or cavewoman physicist, how do you attack such a big question, right? How do we approach the biggest questions in the universe? Well, as a scientist, if you don't know necessarily how to approach it, you just try the dumbest thing first, right? The simplest approach, and then if that doesn't work, then you try the second dumbest thing, etc., till you get a satisfactory answer. Okay, so what is the simplest approach to asking the question, what is the universe made out of? Well, it's not banging rocks together. It might be this. Just say, what's in the universe, right? Let's just make a list. What do we see around us in the universe, right? Well, of course, I'm in the universe. You're in the universe, right? If this is caveman, cavewoman physics, then, we got rocks and these rocks and those other rocks and lots of things that we have to explain in the universe, right? But already you see a lot of problems with this approach. This is definitely not going to be a good answer to the question. Problem number one is there's a lot more than just rocks in the universe, right? There's a lot of amazing things in the universe. The more you look around, the more you realize the universe has, mushrooms and ice cream cones and blueberries. And if you're going to answer this question, what is the universe made out of, you have to explain all of this stuff. You have to explain all the incredible complexity of things that we see around us, right? And the more you look around, the more you hunt at stuff, the more you see there's a really incredible variety. I mean, we have bicycles, we have puppies, we have strangely muscular guys that become governor of California. And apparently there's a statue of him in Columbus for some bizarre reason, right? So it's an incredible universe we live in. I'm glad that it's not just rocks. Eventually that will be me. I'm glad that the universe is not just made out of rocks, but it makes it harder to answer the question. And it makes you wonder, well, what kind of answer do we want to this question? The question of what is the universe made out of? I mean, imagine you were granted by a genie or God or whatever you believe in the answer to one question about the universe. And you asked this question, what is the universe made out of? And they gave you literally a list, right, of everything in the universe, every rock, every particle, whatever. You wouldn't find that satisfactory. You wouldn't think like, oh yeah, I get it, right? Now I understand what the universe is made out of. That's sort of a cop-out answer, right? It's like if you're a teenager and your parents ask you where you're going, you say, out, right? It's like, okay, you answered the question, but you didn't really answer the question, right? So what kind of answer do we want? It's not a list. We don't want to enumerate what's in the universe. We're not botanists, right? We want to reduce the universe down to something simpler. We want to explain all this incredible complexity using just a few basic building blocks, right? We want to peel back a layer of reality and see what's underneath. So how do we get there? Well, we don't just make a list. We organize what we've seen, and we look for patterns, right? So you group the stuff together that's similar. You say, well, the rock-like stuff is over here, and the life-like stuff is over here. And you can argue with me about what category Arnold Schwarzenegger belongs in, right? But everything has to be in a category somewhere. And then you start looking for patterns, and those patterns generate questions. And those questions are clues that lead you to the answer, to figure out what is it underneath, what is happening deep down that explains all those patterns that you see, right? So fast forward a few hundred years, or a few thousand, if you give the Greeks any credit, and you get to the periodic table of the elements, right? Which is prominently displayed on both walls here. And you might be thinking, what? This is supposed to be about particle physics. Why are we hearing about high school chemistry, right? The periodic table. In my view, the periodic table, though it's high school chemistry, is also one of the most underrated intellectual achievements of all time. Why? Because when you're answering this question, you go from infinite complexity down to 100 basic building blocks. The periodic table explains a huge, amazing, dizzying variety of stuff in terms of just a few basic building blocks, right? Down to 100. If your goal is to go from infinite complexity down to one particle or two particles, then you're most of the way there already, right? From infinity to 100 is most of the way. The rest is just details. So the periodic table should get a lot of credit. I mean, it makes you wonder, why is it even possible? Why is it possible for the universe in all of its incredible complex variety to be built out of a few basic building blocks, right? It's almost like the whole universe is just like a big model for the Lego company, right? I mean, this is their basic idea. Out of a few basic building blocks, you can make anything, right? Like, for some reason, the universe seems to follow the Lego philosophy. You can make dinosaurs, you can make pirates, you can make dinosaur pirates, you can make whatever you like using the same building blocks. And that's exactly what allows us to take this reductionist approach, to say, we want to explain all of this complexity using a few simple things, right? There you go, dinosaur pirates. I mean, it could have been different, right? It could have been that everything in the universe was made out of its own kind of particle, right? Maybe cats are made out of their own little weird kind of particle, and that explains their behavior. And llamas are made out of little llama-ninos, and cartoonists out of cartoonons or something, right? That could have been our universe. If you're a caveman or cavewoman physicist, and you're the first person to ask this question, you have to accept any possible answer, right? So this could have been our universe. Fortunately, for us particle physicists, it's not. And it is possible to reduce the universe down to a few basic building blocks. Okay, so we have the periodic table of the elements. But remember, we don't just list our knowledge and say we're done. That's not an answer to the question. We organize what we know, and we look for patterns. Because, of course, those patterns are clues. Those patterns generate questions in our mind, and the answer to those questions will lead us to peel back one more layer of reality and see what's underneath, right? After all, the periodic table is periodic, right? There's patterns in here. There's the heavy stuff and the light stuff and the interactive stuff, and there's cartoonists getting bored and playing Tetris, and all sorts of interesting stuff is happening in the periodic table, right? And all of those patterns are, of course, just clues to tell you what's going on underneath. And I'm sure you know that all the structure in the periodic table comes just from the structure of the atom, right? How the electrons fill the orbitals and how the protons fill in the nucleus. Everything that's happening in the periodic table was just a clue that pointed us to the deeper structure, right? So that's the lesson. You want to figure out what the universe is made out of? You keep listing your knowledge, you organize it, you look for patterns, and you ask questions. And I'm not telling you that to inform you, because I'm sure you know that about the periodic table, but that's the lesson we're going to apply once we get to the forefront of human knowledge to try to peer deeper into the understanding, right? So there's the hula hoop theory, the not very well-known hula hoop theory of fundamental physics. All right, so however, we know that the atom is not the most fundamental building block of the universe, right? In fact, nothing that you know, no familiar, concrete, macroscopic object is anything that explains the universe, right? It's not made out of atoms. It's not made out of llamas. It's not made out of tornadoes, right? It's certainly not made out of llama tornadoes, right, or anything crazy like that. Though, given the way things are going on television, you might see a llama tornado special on Sci-Fi next year. We'll see. Just after Shark Week. So none of these things are the basic building blocks of the universe, right? So let's dig a little deeper. Inside the atom, you have protons and neutrons, right, and electrons whizzing around. Inside the protons and neutrons, you have up quarks and down quarks, which means that with up quarks, down quarks, and electrons, you can build protons and neutrons and then atoms. And with those, you can make anything, right? Which means that with just 3 particles, up quarks, down quarks, and electrons, you can make anything you've ever tasted or touched or interacted with, anything any human has ever seen or sat on or eaten, right? Any of those things are made out of just 3 particles. It's incredible. It's like if you asked a particle physicist to write a cookbook, they would say, oh, well, you just need 3 ingredients for every recipe, right? Up quarks, down quarks, electrons, mix. We're done, right? That's the reductionist recipe book of the universe. And to me, that's fascinating, and it's incredible progress. And you might think, wow, we went from infinity to 100, down to 3. Next week, they'll be down to 1 particle that rules them all, right? And we're certainly making good progress, but we're not quite there yet. We have a lot of questions remaining about these particles. Now let's talk about that. One reason is that these aren't the only particles we've found, right? There's the up quark, the down quark, and the electron, but there are also other quarks. There are 4 other quarks. The charm quark, the strange quark, the top quark, and the bottom quark, right? Not responsible for the naming of these particles, okay? And the electron is an example of a lepton, of which there are 5 other leptons, right? So there's these 12 particles. But again, we don't just list our knowledge and say, okay, we're done, we answered the question. The universe is made out of these 12 particles. No, we organize it and we look for patterns, right? So now we have a new table, a fundamental table, a periodic table of the fundamental particles, right? That expresses everything we know about these particles and raises questions. Those questions are the clues to getting deeper and deeper. So let's take a look at this table for a moment. You have the up quark, the down quark, and the electron. These are the three particles you need to make matter, right? Excellent. But down here you also have this particle, the electron neutrino, which is a really mysterious little particle. Not mysterious because it's rare. On the contrary, there's 100 billion neutrinos passing through your fingernail every second, right? Every second, 100 billion, 200 billion, 300 billion. It's incredible the number of neutrinos. So why are we not all beaten down by all the neutrino radiation, right? Because we don't feel neutrinos, and neutrinos don't feel us. They almost never interact with us. In fact, a neutrino can go through a light year of lead, right? Imagine a wall that's a light year thick. That's a really, really thick wall. A neutrino can fly right through that and hardly notice. So neutrinos are like a separate universe on top of us, on top of ours, that we hardly ever interact with. It's a clue that there's a lot of things happening in the universe that we never see, or that you never see. Okay, so we have those 4 particles, and they're all different. Now we take the other 8 particles, and we notice something. Those other 8 particles are actually just copies of the first 4 particles. For example, the charm quark and the top quark are exact copies of the up quark. They have the same charge, they have the same spin, they have the same interactions, okay? Except the charm is heavier than the up quark. It's like the up quark's secret fat cousin or something, right? And the top quark is even heavier. It's incredibly massive. It's like the up quark is a second super secret cousin that can't even leave the house. It's when it's so big, it can't even get through the door. Don't be offended, top quark. And the same thing is true for the other particles, okay? The strange is a copy of the down. The bottom is another copy of the down. And each of the particles in the first column seems to have 2 copies, right? The muon and the tau follow the same pattern, and the neutrinos, there are even 3 of those. Though we're a little less clear so far on exactly the mass relationship. But there's a lot of patterns here in this periodic table. And those patterns lead to questions, right? And those questions, we hope those questions will lead us to answers. What's underneath this table? The structure of this periodic table, we think, is clues that tell us what's making all these particles, right? Just the same way the structure of the periodic table gave us clues about the atom, we hope this table's structure will give us clues about what's underneath. So, what kind of questions do we ask? Well, pretty simple questions, like, why do we have all these particles, right? You only need a few, 3 of them to make matter. Why do we have 12? We have no idea the answer to that question. Do we in fact have 12? Are there 12? Are there 12,000? Are there 12 million kinds of particles? Theoretical physics puts no limit on the number of particles that could exist. So either this is the whole ice cube or just the tip of the iceberg, right? We have no idea. Why are some of these particles heavy and some of them light? The Higgs boson is responsible for giving these particles mass, but we don't know why it gives the top quark a huge amount of mass and the electron only a tiny little bit. Right? There's no explanation in the Higgs boson theory for why it interacts a lot with some particles and not very much at all with other particles. Totally unanswered question. One of my favorites has to do with the really strange little charges of these particles. So for example, the up quarks and the down quark have these fractional charges, which you might think is kind of weird, a fractional charge. But if you add them up, the up quark and the down quark, you get a proton with charge +1, which is awfully convenient because the electron is charged -1, right? So the 2 things balance each other out very nicely. You can get neutral atoms, you can get chemistry, you get biology, you get silly physics books, you get ice cream, whatever you like, right? All of that reflects the fact that these 2 things balance. However, in our current theory, that's an accident. Right? The charge of the quarks and the charge of the leptons have no relationship in our current theory. If you're at the control panel of the universe, you could dial those up and down independently. Right? So either it's a huge coincidence, right? It's just totally random that these 2 numbers exactly balance each other, or it's a clue, right? It's a clue that deep down they're made out of the same kind of thing. There's a relationship between them we don't understand. They're 2 sides of the same coin, right? To me, this is so tantalizing because it screams, clue, 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 right? And we're like, well, we get that there's a clue, but what does it mean, right? In 100 years, people will be reading about this in textbooks and they'll say, it was so obvious, come on. If I'd been a physicist in 2017, I could have written that paper and got a Nobel Prize, no problem, right? But when you're here at the forefront of human ignorance, you could tell it's a clue. You don't know which way to go. It's much harder to figure these things out, right? So we don't just think about the matter particles also, we also think about how the particles interact with each other, how they talk to each other. And before Jorge was the favorite cartoonist of particle physics, we had Richard Feynman, who came up with a sort of cartoony way to think about particles, which is the Feynman diagram. And in a Feynman diagram, the solid lines are matter particles, and the wiggles between them are how they talk to each other. And he came up with this way of thinking about how they talk to each other using cartoons, and we use that strategy now to make calculations about how particles bounce off each other and interact with each other. The incredible thing about these calculations is that they're super duper duper accurate. We can make a prediction and then go into the lab and measure that thing we predicted and get the same answer to many, many decimal places, 9, 10 decimal places. If you're an experimentalist, right, you know that if you make a prediction about your experiment and then you go and do it and you get an answer within a factor of 2, you're like, yes, I can go home and watch Netflix. This is 10 decimal places. That doesn't happen by chance, right? The probability of that happening by chance is like the probability of hitting a golf ball in New York and getting a hole-in-one in China, right? It just doesn't happen by chance. It tells you we've really figured out something deep, something fundamentally true about how these particles interact with each other. Okay, but we don't just judge a theory by whether or not it's accurate, right? It certainly is accurate. We also want a simple theory. One of the goals of particle physics is to have a whole theory of the universe boiled down into an equation that fits on a t-shirt, right? If you can fit it on a t-shirt, then maybe, you're done. And so here is the standard model of particle physics, okay? The current equation. Actually, you have to leave out half of the terms. And it's like, you might think we're a little ways away from fitting this onto a t-shirt, unless you're willing to wear the extra, 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 extra large version of the standard model t-shirt, right? Which will be for sale on our website next week, right, Jorge? All right, so we have a little bit of ways to go. But if you're going to answer the question, what is the universe made out of? The biggest problem in answering that question is that everything we've talked about, all of human knowledge about chemistry and physics and all of this stuff, only relates to a tiny little slice of the universe. The tiny slice of the universe that is made out of me and you and planets and stars and gas and dust and all of that stuff is less than 5% of the universe. So if you're going to answer the question, what is the universe made out of, you better address the rest of it as well, right? And to me, this is an incredible moment in physics because we've measured this number, what fraction of the universe is made out of our kind of matter, and it can be explained by up quarks and down quarks and electrons. What fraction of the universe is this? We've measured this very precisely, which means that we're in an era of precision ignorance, right? Where we've measured very, very well exactly how little we know about the universe. And to me, that's not depressing. That's not like, oh my God, look, we spent all this time, we only figured out a little bit. To me, that's exciting, right? Because it means, look at all the crazy things we have left to discover, right? All those great scientists who came before us, they just barely got started. They only scratched the surface, right? There's a huge amount of stuff left to discover. Okay, so you might be wondering, how is it possible that we could know how little we know without knowing what we don't know, right? It seems like a logic puzzle. So we do have some clues about what the rest of the universe is. One of the most important clues came by looking at how galaxies spin. So you can think of a galaxy as like a massive cosmic merry-go-round with a bunch of ping pong balls in it, right? What happens if you spin a merry-go-round with ping pong balls on it? Well, the ping pong balls are going to fly out, right? Unless there's some force holding them in. So in the case of galaxies, that force is gravity. It keeps the stars from flying out into outer space. So now you can do something really interesting, which is you can look at galaxies and you can say, how fast are they spinning? Is there enough gravity to hold those galaxies together, right? You can measure two things and compare them. So somebody sent their graduate student off to do this, say, go check and make sure this actually works out, right? Probably a Friday afternoon at 5 p.m. or something. Go check this number and make sure it works. Well, they went out and they checked it and they came back and said, this doesn't work like at all, okay? Not even close. Turns out these galaxies are spinning much, much faster than we understood. There's not nearly enough gravity to hold the stars in the galaxies, right? So, but we know the galaxies are not throwing stars into interstellar space all the time, right? Something's holding the galaxy together. So they said, well, there has to be some other form of gravity that's adding to it, something we can't see but gives gravity, right? So they came up with this theory of dark matter. Dark meaning we can't see it. Matter meaning it gives gravity, right? This is a very clever trick in physics. You take a huge mystery and you turn it into a theory. You say, what could be responsible for invisibly giving us new gravity, right? Well, how about some invisible new gravity-giving thing? Yeah, and that's what dark matter is, right? That's really all that it is. Dark matter means dark is invisible, matter and gives us gravity. So they had to do this to explain how these galaxies are spinning. So before we go on, let's think for a moment about exactly what dark means. Dark means that we can't see it, we can't interact with it, but there's 4 ways that particles can interact with each other. One is gravity, right? Things that have mass attract each other. The other is electromagnetism. Anything that gives off light or reflects light feels electromagnetism. Then there's the strong and the weak nuclear forces that hold the nucleus together or break it up. So in the case of dark matter, we know that it feels gravity, right? We invented the idea of dark matter, the concept, in order to explain the missing gravity. We know it doesn't feel electromagnetism. It's dark, right? It's invisible. It doesn't feel the weak force. It doesn't feel the strong force. As far as we know, dark matter has no other interactions. It may be that there's some kind of interaction we haven't detected yet, but as far as we can tell, we do not know that dark matter interacts in any other way, right? It's not even on social media, right? I've sent it zillions of Facebook requests. It never responds, okay? So there's no way to interact with dark matter other than gravity that we know of so far. So all the stuff in the universe that we know, that we're familiar with, is 5% of the universe. To explain how fast these galaxies are spinning, you don't just have to add a little bit, like 1 or 2 or 3% extra gravity to these galaxies. You have to add a huge amount. You have to add 5 times as much normal matter, right? Dark matter is not just a little sliver of the universe. There's 5 times as much dark matter as there is normal matter, which means we're not normal matter, right? We're unusual matter. We're abnormal matter. We're a tiny little unusual slice of the universe. And before people were willing to believe this crazy idea, like, so your experiment doesn't make sense, and you're postulating an incredible amount of matter that invisibly fills the universe to explain why your experiment doesn't make sense, right? Maybe you should go and check the numbers. So before people were really willing to believe this crazy idea, they had to find other ways to see dark matter. One of the coolest ways they had to see dark matter is by using it as a lens, gravitational lensing. So dark matter is dark, it's invisible, light passes through it, but it feels gravity, it has mass, so it can bend space and act like a lens. So imagine there's some big blob of dark matter between you and some other galaxy, and a photon shoots out from that galaxy, and it gets bent towards your telescope, right? And then at the same time, another photon shoots out from the galaxy in another direction and gets bent also towards your telescope. That means you look at 2 different places in the sky and you see the same galaxy, right? That's crazy. It means either you've been smoking too many banana peels, right? Or there's something invisible in the sky out there that's bending the light, acting like a huge cosmic lens, right? So that was another really good clue about dark matter. But the most important clue, in my opinion, came from this massive collision. So I'm a particle physicist, which means I like to solve problems by smashing stuff together, right? You ask me, Daniel, how does this toaster work? I'll say, well, let's smash 2 of them together and figure it out, right? That's my go-to approach. However, in the case of cosmic-sized objects, you can't really do that. You can't go to the National Science Foundation and say, I want to build a galaxy collider, right? How much does it cost? Oh, $10 trillion, you know? It's not going to get funded. So astrophysicists have a different approach. Instead of building experiments, they just look out into the universe and find one that's already happening, because the universe is huge and full of crazy stuff, right? So they found this experiment that was going on, which is 2 clusters of galaxies smashing into each other, and they took advantage. Because what happens when clusters of galaxies smash into each other? Well, each cluster has normal matter and dark matter on top of each other, right? And when they smash into each other, the normal matter makes huge explosions, boom, 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 like a Transformers movie, but the dark matter passes right through, because it doesn't interact, as far as we know. It may have some low-level interactions, but as far as we can tell, it just passed right through. Now, we can see where the dark matter is using gravitational lensing. We can see where the normal matter is. It's normal matter, after all. And so they got separated. And so we can measure the gravitational feeling of the dark matter on its own, right? It got separated from the normal matter. So we know it's not just a misunderstanding of how gravity works for normal matter. Dark matter really is its own thing with its own kind of gravity, right? What is that thing? We still don't know. But this, to me, was really a smoking gun piece of evidence that dark matter did exist. But what is dark matter, right? We still don't know the answer to that question. And the reason I haven't told you the answer is that I don't know the answer. Nobody knows the answer, right? We have no idea what dark matter is. Dark matter could be made out of just one little kind of particle that hardly interacts. A favorite theory among physicists is called weakly interacting massive particle, right? If you put that together, it's WIMPs, right? Maybe dark matter is just a bunch of WIMPs out there and not interacting with anybody. That could be, but it's sort of the most boring possible answer, right? I like to think maybe dark matter is really complicated. Maybe it has like 5 different, 10 different kind of particles, and those particles interact with each other the way our particles do, right? It could be that there's dark physics and dark chemistry. There could even be dark life, right? After all, we're a tiny little slice of the universe, right? Somewhere out there, there could be a dark physicist giving a dark talk about how we understand 95% of the universe except for this little sliver, right? That sliver is us, okay? So the other thing to remember about dark matter is that it's not out there, it's far away in the universe. It's here with us, right? We have dark matter in this room with us right now. Dark matter and normal matter follow the same patterns, and it's not an accident. We just can't interact with it the way we can't interact with neutrinos, right? So dark matter is here with us, and it outnumbers us. Okay, so 5% of the universe is stuff we know. 27% is this mysterious, unknown, we have no idea matter called dark matter. The rest of the universe, 68%, what is that? If we're going to answer the question, what's the universe made out of, we at least have to get up to halfway, right, to claim to know anything. Well, this last fraction we call dark energy, but that's really just science code for we have no clue what this part of the universe is, right? We call it dark energy, but dark energy and dark matter, don't be confused, they have no relationship other than literally the word dark, okay? There's no clues about dark energy from dark matter. So how do we know what dark energy is? Or how do we know that it's there and how much of it there is? Well, people went out to try to understand the future of the universe. And to understand the future of the universe, you have to know a little bit about the history of the universe. So here's a crash course in the history of the universe, right? In the very beginning of time, there was the Big Bang, okay? And then a bunch of stuff happened, you know, and interesting stuff happened. And the stuff was all flying out from the Big Bang, and people had this question: what's going to happen? Is there enough stuff and enough gravity in the universe that things would slow down, stop, turn around, and come back, right? Making a big crunch was option A for the universe. Option B was that things flew out from the Big Bang, slowed down, but never enough to turn around, just sort of gradually drift off, cooling down forever and spreading out to something cozily called the heat death of the universe, right? So option 1 was the big crunch. Option 2 was the heat death of the universe. People went out to measure this. They figured out really clever ways to see whether things were moving away from us faster now than they were in the past, or more slowly, or how these things were changing. And what they figured out was a huge surprise. The universe actually goes for secret option C, okay? Secret option C is, after the Big Bang, things didn't slow down at all. In fact, they sped up. Things are moving away from each other faster and faster, right? The expansion of the universe is not decreasing, it's accelerating. And you might be thinking, accelerating? How is that even possible, right? What could be responsible for accelerating the expansion of the universe, for pushing galaxies apart, right? It's not an easy thing to do, to push an entire galaxy with hundreds of billions of stars, right? It takes an enormous amount of energy, something like, I don't know, 2/3 of the energy in the universe, right? And that's exactly what's happening. Some mysterious force is ripping the universe apart. It's creating new space between our galaxy and other galaxies. What is it? We don't know. Why is it doing it? We have no idea. Will it keep doing it in the future? We don't know, right? We do know it turned on about 5 billion years ago, dark energy, and that it's accelerating the expansion of the universe, but we don't know what's going to happen in the future, which means it's hard to predict, for example, what the future night sky will look like, right? It may be, if dark energy continues, and that's just speculation, that because new space is being created between us and other galaxies faster than light can move through that space, right? Faster than light can move through that space. That's like Usain Bolt is running at you really fast, and somebody's laying new track in front of him faster than he's running, so he never gets to you, right? Doesn't matter what the speed of light is. If you're making new space between us and other galaxies, that light will never reach us, which means these galaxies are going to disappear over our visible horizon. So they're just going to, disappear slowly, and the night sky will get darker and darker and darker. If dark energy is strong enough, it might even be able to rip our galaxy apart, and then stars will start to disappear, right? In some version of the future, astronomers could look up in the night sky, right? I like to fantasize that in 10 billion years we still will have humanity and we'll still be doing astronomy. In 10 billion years, people might look up at the night sky and see something totally dark. Right? How could they possibly even figure out anything about the universe if they can't see anything in the night sky? Think of all the things we've learned by looking at stars and everything in the sky. If it's totally black, you'd be totally clueless, right? So you might be thinking, I'm glad that we live now, right, when we have all this information in the night sky. It's true, we do see a lot of stuff, but what are we missing? We're 14 billion years into the history of the universe already, right? What existed in the night sky 10 billion years ago, which is now lost to us forever? Well, we have no idea, and we may never know. So here's a summary of our knowledge of the universe. Most of the universe is something we only recently discovered we have no idea about. Okay? The dark energy is the biggest part of the energy budget of the universe, and yet we know almost nothing about it, and we only recently figured that out. Okay? Dark matter we've known about for a few more decades. We have a few more clues about, but we're still pretty clueless when it comes to the details of what dark matter is and how it works and why it's there. And the rest of the universe, me, you, and dark chocolate, that's really the et cetera, right? You could almost round up from dark matter and dark energy to the rest of the universe and just ignore our little bit, right? So think about that when you think about how much we know about the universe and what you can expect to think about the future. Can we extrapolate from a tiny little slice of the universe to understanding the rest of it? Can we pretend to say, oh, we've mostly figured it out and the rest are details, right? I think that what we have ahead of us to learn are crazy ideas. Imagine, for example, you've been studying an elephant for 300 years, but you only focused on the tail. Until finally somebody walks you around to the front of the elephant and says, maybe you should look at the rest of the elephant before you draw some conclusions, okay? If you're a physicist, your inclination is going to be, well, I can model the whole elephant as a linear combination of tails or something, or like a perturbation on the tail theory or something crazy, right? That's going to be your inclination because that's what physics is, right? Describe the unknown in terms of the known. It sounds like a dumb idea, right? That's exactly the same as what I said earlier. Maybe dark matter is made out of particles. Why? Well, because everything else we've seen is made out of particles. Yeah, but everything else we've seen is just the tail of the universe. So I think this represents a moment in physics when we can have not just some new discoveries, but like a revolution, right? Completely changing the way we think about the universe, right? So I hope that the future has really exciting things to tell us, right? This is the time to like throw away everything we thought we knew and start fresh and not clutter our minds with the preconceived notions from everything we thought we knew about the elephant's tail. So we're doing everything we can to figure this stuff out, right? We have space telescopes, we have gravitational wave detectors, we have amazing particle physics detectors to smash matter and rip it apart and try to understand it. We're hoping to figure this stuff out. I hope that we figure it out soon, right? Before the aliens arrive and just tell us the answers. That would be disappointing, right? And I also like to think that these are the days we might figure this stuff out, that people might look back on 2017 or 2020 and say, wow, I wish I had been a physicist back then, back when they figured out these basic questions about the universe. I also think in 1,000 years, people will look back and wonder, what was it like to live in such ignorance, right? Because they will know the answer to basic questions about the universe we don't know. How did it start? How will it end? What is it made out of, right? Basic things about our existence we don't know the answers to. Think about the way you imagine cavemen and cavewomen, right? They were totally clueless. They didn't know anything about the universe. They looked up at the night sky. They had no idea how much information was washing over them all the time, right? They didn't even know what stars were, right? They were totally clueless. That's us, okay? We're still at that level of fractional knowledge about the universe. In 1,000 years, a children's book, right, a kindergarten book about the universe will reveal facts about the universe that we have no idea about, that would blow our minds if we knew them. I would love to travel forward in the future and steal a kindergarten book about astronomy, you know? Wow, what revelations would exist there? I can't even imagine. So that's what our book is about. And in the book, we talk about this question, what is the universe made out of? But also other really big, very basic questions about the universe. Questions like, what is space? Okay, to me, this is a really fun question. Because for the longest time, we thought, oh, space is just emptiness, right? Just the backdrop on which the universe takes place, right? Except that space can expand, right? That's dark energy. Space can bend. That's what gravity does. Space can even ripple, right? That's what gravitational waves are. So space is complicated. Space is a thing, right? It's not just the emptiness. It's like if you were a fish scientist And you've been swimming through water for 1,000 years thinking, oh, the water's not important, it's just the nothing, right? And then somebody shows you, oh, it can boil, and it has an edge, and all sorts of weird stuff, right? That's where we are with space. We only recently figured out this is an interesting, important, and difficult question we don't know the answer to. And it's the same with questions like, what is time? Or how many directions are there of space, right? We're at the very beginning of answering these questions. But the answers are out there. There is an answer to these questions. Someday somebody will figure them out. So the point of our book is not to tell you science doesn't know anything, right? It's just to tell you the science is the beginning of the journey. And we hope that you or your kids or our grandkids or somebody will figure out the answer to these big questions. So thanks for listening. And if anybody has questions about physics or cartooning or something else?
Why don't we give them a chance to take questions? And here, I want to take this one.
Yes, sir.
So there is no such thing as vacuum?
The short answer is no. The technical answer is it depends very closely on what you define as a vacuum. But if you think of vacuum as perfectly empty space, then no. There's an energy in space, even in space that you think has no matter in it, and that energy is constantly turning into particles and turning back into energy. There is no space without any energy in it. Yeah. However, we don't know how big space is, right? The universe, we don't know. Is it infinite or is it finite? It could be finite, which means there could be an edge of space, right? What does that even mean, an edge of space? What is beyond space? The non-space? The space of space? Like, I mean, those questions are at the point, they're like, it's metaphysics at this point, right? Any idea you have is just speculation. But these are real questions, right? It's exciting. Yes, sir.
It seems to be a reoccurring theme that people like to bring up that everything we know is based on particle interactions, whether EM or whatever, and we're now delving into gravitational detection with LIGO and stuff like that. Do you see any interesting avenues that could produce outside of just detecting big neutron stars colliding?
Yeah, so the question is, can we learn things about the universe other than just by particles interacting, but by things like gravitational waves and looking at the universe in other ways? Absolutely. Gravitational waves are a totally new way to look at the universe, and we've only just recently opened our eyes, right? And we've seen a few little blips, and so we have no idea what's out there, and gravitational waves will bring a lot of surprises. And you raise another interesting question, which is, we talk about all the interactions in terms of particles. Electromagnetism is transmitted with photons, etc. Gravity, however, we don't have an understanding of gravity in terms of particles, right? We have a good understanding of gravity in terms of space being bent by mass and general relativity, but we have no way to unify general relativity with our otherwise quantum picture of the universe. So one awesome thing about seeing gravitational waves is that it might give us some more clues about how to bring gravity sort of into the family of quantum interactions. So far, we have no idea. Great question. Tim.
Yeah. The question is, on a physics paper, you can write as long as you want. You can write a 70-page paper. Is that kind of what you mean? Yeah, but for a book or a cartoon, you sort of have to figure out what to cut out and what not to cut out. So how do we think about that? Is that what you mean? Yeah. For this book, it helped a lot that each chapter is like a different big question about the universe. And so that really sort of helped us focus the topic and what to talk about and what not to talk about. So for example, a question would be like, how big is the universe? And so that really helped us figure out like, all right, the goal of the chapter is to communicate what we know about this question. What are the things we don't know about the size of the universe? What are the things we do know about the size of the universe? And so that, I think that was part of what helped us kind of navigate. Well, we don't really need to talk about this, or we don't, or this thing about this topic we could maybe expand into another chapter. So yeah, just having each chapter kind of deal with a question really helped us.
And Jorge's also being polite. I pontificated like crazy, and then he just deleted a lot of stuff that I wrote. And jokes aside, that was really a good process, because I would write a bunch of stuff, and he would say, well, I think this is the interesting bit, or this stuff's not really relevant, even though you're interested in it, Daniel. So it was a really useful process to go back and forth.
Yeah.
Okay, well, we'll be here. If you want to buy a book, it's outside, and we'll be here signing copies if you have them, or if you're too shy to ask a question in public, come on up and ask us in person.
So on behalf of all of us, let's thank Jorge and Daniel. Thanks very much for your time, interest, and attention, and we hope to see you at future CCAPP events or Science Sundays events or the Physics Smith Lecture, things like that. So there should be books for sale, and you have a chance to come talk to the authors and get your books signed. Thanks, everybody. Bye-bye.